Okay, very good. So, yeah, first I realized I forgot to mention something before. So this automatic documentation, deoxygen, was actually a lot of work. It's a lot of work to have everything working in the right syntax and not broken. And the person who has developed this deoxygen documentation is my PhD student, Diana Hooper, who is finishing her PhD now. And I forgot also to include her name in the slides, but it's a very good work that should be acknowledged. Also, some people, of course, every time there is a workshop like this, some people have weird problem on their laptop that I've never seen before. And the best is to help each other in these cases, because most of you, being younger, are much better than me in fixing installation problem. So for instance, here we have a problem of somebody. You can raise your hand. So it's Kara, right? Kara can compile the Python module and open it in a terminal. But when she tries with Jupyter, it says class C not installed, while from the terminal it works. If you had a similar problem and you know how to solve it, you can talk with her. Very good. It's like in Anonymous Alcoholics. I'm trying to put people with problems in contact. Yeah. So class theory, there will be a little bit more of physics now, starting from very, very easy things because you have very different levels. Some of you are more large-scale structure, some are more CMB, some are just discovering cosmology, some are experts. I have to take all these things into account. So we will start with the part one, which is more basic, which are the essential step in an Einstein-Boltzmann solver. So for an expert, this would be very basic, but even for an expert, sometimes seeing these things rings a bell and generates some questions. And after going through these essential steps, we will go into more details into each of them. And I will mention what is non-trivial, what you might not know, and what are the assumptions that are different in class than in other codes. Okay, so an Einstein-Boltzmann solver will always go through a series of steps that I have labeled here from A to H. So step A is the integration of the background. The code must integrate the homogeneous universe, the background cosmology, as a function of time. And this will be done in class as a function of conformal time that I will always denote tau. It's done mainly after integrating one equation, which is the Friedmann equation. Once you have done this, you have the correspondence between A and tau, and there is always a trivial correspondence between A and Z. So then you can convert a tau in a Z in a tau, etc. We will see that the module also keeps track of proper time, so you have even a correspondence between these four ways to label the time evolution. Okay, so this is a trivial task. Another one, which is far less trivial, is to get the evolution of all the thermodynamical quantities as a function of a time variable. And in the case of class, and actually also of COMB, now you switch of time variable, you use Z, the redshift. It's not a problem because in the previous step, you established a correspondence, a mapping between tau and Z. So now you can choose whatever you want. And for this, you must integrate some differential equations, simulating the recombination and the reionization at various levels. So the most important of these equations will be a differential equation for the evolution of the ionization fraction in the universe as a function of redshift. Once you have it, you can compute important derived quantity. You can compute directly by multiplying with something the Thomson scattering rate, denoted kappa prime. It's denoted kappa prime because the integral of this guy, denoted kappa, is the optical depth, and very important in the CMB formulas. So sometimes, the most common way to write the optical depth is a tau. For instance, tau reionization is a well-known parameter. But this would lead to some ambiguity in the code and in the lecture between optical depth and conformal time. So in the code and in the lecture, it's kappa for optical depth, tau for conformal time. This is actually used by other authors. Mann, Bertschinger also use a kappa. Once you have kappa, you derive the exponential of minus kappa. It will be a prefactor when we will compute the integrated Sachs-Wolfe effect, which is a component of the CMB. And then this exponential minus kappa times kappa prime will give you the visibility function, which is a prefactor in CMB formulas when you want to compute, for instance, the main CMB effect, which comes from the Sachs-Wolfe formula. And once you have the visibility function, you want to compute its derivative. It will be used for the Doppler effect in the CMB. So the role of the thermodynamics module is to get all these quantities. A bit later, we will go a little bit into details, and I will show you that you can choose between various codes to achieve this. The next one is a perturbation step. So these steps will become module in the code. So it will be the perturbation module. And the goal now is to find the evolution of each perturbation for each Fourier mode. So this can be density fluctuation, metric fluctuation, pressure fluctuations. And for that, you need to integrate a system of coupled ordinary differential equations for each independent wave number. Of course, they are independent because we are doing linear theory. And you need to do it also for, not just for each wave number, but if you have a complicated cosmology, you will need to do it for each mode. And for me, most of the time, mode will not mean Fourier mode. We'll try to say wave number otherwise. Mode will mean the scalar, vector, and tensor modes of Bardeen. So the three ways to decompose your perturbation in three decoupled sectors at the linear level. And there is another loop to do, because sometimes you don't need to loop just over K and modes, but also initial conditions, going through the adiabatic initial condition and different types of isocurvature initial conditions. You know what this is if you are working more in the direction of inflation and early universe physics. A note on the vectors. So you know the vectors are rarely useful in cosmology because even if you excite them, they decay, so you don't care at the end. They are useful in very special types of cosmology, for instance, when you have topological defects. But topological defects are not covered by the default class, although there is a group working on this also. But so we decided that we would write the vector equation in the module, just in case somebody needs them. But we don't have a concrete application for these vector modes, so we don't have a function with initial condition for them, and we don't include them in the output so far. But it would be easy to modify. Okay, so in summary, you have a triple loop. And for each occurrence of this loop, you have to integrate one big system of coupled differential equation. And these equations are Boltzmann equation for fluid described by a phase-space distribution. These are photon, temperature and polarization, massive and massless neutrinos, or more generally, non-cold dark matter. Then for perfect fluid perturbation, you want to follow a continuity and an Euler equation. There are just three. It's much simpler. And with this, you will describe baryons, cold dark matter, and some hypothetical fluid that you can use in class to model either dark energy or some funny dark matter or some self-interacting dark radiation fluid. And the condition for using continuity and Euler equation is either that you have a perfect fluid or an approximatively pressureless species like cold dark matter. So these two give you the evolution equation for all matter perturbations of all types. But to close the system, you still need to use the linearized Einstein equations. Now, you know that, for instance, for scalar modes, the linearized Einstein equation gives you four equations. And a big question is always how to use them. Do I use them as additional second-order differential equation as really a degree of freedom that I must integrate over time together with the other ones and increasing the size of my system of differential equation? Or should I use them as constraint equation, meaning I keep the same number of differential equations, but in this equation I see the metric perturbation phi m psi, and I get them out of the matter fluctuations from the linear equation, from the Einstein equation. So when Einstein equations are constraint equations, it means they are not a new degree of freedom that I integrate, but they are a way just to close the system. So in synchronous gauge, it's obvious that one of the Einstein equations must be used as a differential equation, and the other are constraint equations. In the Newtonian gauge, there is an interesting discussion. In the Newtonian gauge, you could choose to use all Einstein equations as constraint equations, but for reasons of numerical stability, you realize that it is still better to use one of these Einstein equations as a differential equation. So in all our gauges, the Einstein equation gives you one differential equation and three constraint equations. Okay, now suppose you have everything ready to integrate the system. You need some initial conditions. And the trick used in all Boltzmann codes is very basic. It's the fact that since this is a linear perturbation theory, the output depends linearly on the initial conditions, the constant of integration that you put as initial conditions. And it allows you to separate the problem. First, you choose initial conditions. Then you integrate your system from arbitrary initial conditions. And then you put all the information together when you want to compute the final observables. This is very convenient. It means that at this stage, even if we have not discussed the primordial perturbation yet, we can integrate our equation starting from an arbitrary normalization. And later on, we will multiply by something in order to make the initial condition realistic. So in the language of cosmological perturbation theory, it means that what we are going to solve here are not the actual perturbations, but the transfer functions, which means the perturbation normalized to an arbitrary initial condition. And both Com and Class make the following choice. In CMB-Fast, it was different. If you are interested in the scalar perturbation and in the adiabatic mode, the initial conditions here will be a curvature perturbation set to 1. So you integrate the system starting from r equal 1. And it's really not a problem because later on we will multiply the square of the transfer function by the primordial spectrum of R. Okay, so there are other conventions when you have entropy or isocurvature modes and tensor modes. Okay, so when I will use the word transfer function, very often it will mean this perturbation normalized to r equal 1. So once, this is not the only task of the module. Once the module has solved all these equations, you could think that the module must store all these variables as a function of tau and k. It would be a very big output, but it's not needed. What the code must do is only keep in memory the quantities which will be important for the final calculation of the output. Sometimes these are raw transfer functions. For instance, the code will compute the fluctuation of baryon and cold dark matter. It will be a delta B of time and k, a delta CDM of time and k. And then you just add them together with some weights in front. You get the perturbations of matter, and this will be directly useful to get the matter power spectrum. Sometimes what you want to keep in memory is a non-trivial combination. If you want to compute your CMB, you must assemble your transfer function in a more complicated function which knows about the photon perturbation, the baryon perturbation, the metric perturbation, and some function of the thermodynamical evolution. And these are the famous CMB source functions. And ST would be the source function for the temperature of the CMB. I will show an equation later on. So you see that the code is not going to keep in memory all the transfer function, but only the combination that are needed. If you ask for the matter power spectrum, it will keep this delta M. If you ask for the CMB, it will keep in memory all these CMB source functions. Sometimes you just want to see all the transfer function of all variables. Then there is a flag to get this, and then in this case, all the deltas will be kept in memory, otherwise not. There is also a flag to keep in memory the transfer function of all the velocities, which are called theta in Mah and Bertschinger notations. So there is a flag to turn on this velocity transfer function, and only then the code will keep in memory all the thetas. Okay, so this is the task of the perturbation module. Integrate all perturbation, keep in memory the source function. And source function for in the language of class is anything that you keep in memory after this stage, and they are always function of tau and k. I see I've not used the same order, it doesn't matter. They are all function of tau and k. After this step, or before, it's a matter of taste, you have to think about primordial spectra. So the order of the sequence is not unique. You have to start from A and B, but this D could have been before C. So there are some dependencies, but there is not a unique order. D is precisely the module in which you have to think about initial conditions. So for scalar modes, you have adiabatic and isocurvature initial conditions. For gravitational wave, you have tensor initial conditions. And because we are doing linear perturbation theory, and we assume some standard inflation to start with, each perturbation has independent Fourier mode with a Gaussian perturbation. So all the information is stored in the two-point correlation functions or power spectra. So what we must do at this stage is assume a power spectrum for each mode, adiabatic, isocurvature, tensor, and sometimes there will be cross-correlation. There will be a power spectrum of the cross-correlation between the adiabatic mode and the baryon isocurvature mode, for instance. So all this is dealt in a module which has two possible modes. In analytic mode, the module will just try to infer from your input some analytic function for the power law. For instance, the most simple in lambda CDM is to say that you only have scalar adiabatic mode with a k to the power n multiplied by an amplitude a. So this is the analytic mode in the simplest case. In the analytic mode, you can still assume more complicated function with running, with oscillations, whatever. Instead, if you switch to inflation mode, then you give a new task to the code. The code will expect to be given an inflaton potential, and it will integrate over the background and perturbation equations during inflation in order to compute numerically the primordial, scalar, and tensor spectrum. And this spectrum might have features, for instance, if there is a break in the inflaton potential, it can generate features in the primordial spectrum. So this is coded in class since a long time, but only for single field inflation. If you want multiple field inflation, you should replace this part by more sophisticated code like the mode code of Irania-Peiris. For single field, I think this will usually be sufficient. So for instance, in the Planck paper, if you read them, you might have seen plots with isocurvature modes or plots with a reconstruction of the potential of the inflaton, and they have all been done with the primordial spectrum of class, using either the analytic mode for the isocurvature mode plot or the inflation mode in order to reconstruct this inflaton potential. Okay, once you have both the perturbations and the primordial spectra, you can combine them in order to get observables, power spectra in Fourier space. So for instance, the linear matter power spectrum is the square of the matter transfer function multiplied by the primordial spectrum. So assembling information from C and D, you get E. So this is what this module should do, and it will give you the linear matter power spectrum. It will infer from it quantities like sigma, the variance of fluctuation in real space in a sphere of a given radius, including the famous sigma 8 that astrophysicists like so much. And if you have massive neutrinos, it will do the same with this baryon plus cold dark matter component only, which is a better tracer of galaxy correlation and cluster formation. So you will also get a sigma CB8 in this case. If you want some approximation of the nonlinear power spectrum, it will also, at this stage, it will be able to compute nonlinear corrections, for instance, with allofit. As I will tell you tomorrow, HM code is something we have implemented internally a long time ago, but we still did not make it public. I will tell you why, but it will come very soon this summer, I think. After this step, if you have the linear power spectrum and the nonlinear one, it could be clever to compute this kind of factor. It's a nonlinear correction. Let me define my nonlinear correction R as a square root of the ratio between PMNL and PM, linear. So this is by how much I should correct my linear fluctuation delta to capture the nonlinear effects. It's useful to keep this in memory because later on, if I want to compute observables for cosmic shear or for galaxy clustering or even for CMB lensing, and I want to approximate the nonlinear evolution, I will multiply my quantities with this factor later on. So a role of this step will also be to keep in memory these factors, which are a function of wave number and time or wave number and redshift. Okay, and after this, we are done with all the observables in Fourier space, and we want observables in harmonic space, in multiple space, if we want to describe spectra on the sphere, on the sky. So then we need to go through a module F, which is going to translate the transfer function from Fourier space to harmonic space. It will do a kind of projection. I will compute a function which tells me how Fourier modes located at a given distance, for instance, on the last scattering surface, contribute to a given multiple L subtending an angle theta. Okay, so the goal now will be to compute this harmonic transfer function delta L k of x. So it's a projection of mod k to multiple L for a type x. And x, if we are thinking first only about the CMB, could be temperature, E mode, and B modes. And in fact, there is one of these for scalar, one for tensor, and one for each initial conditions. And another way to see this transfer function, for instance, the transfer function of the photon temperature is just the transfer function of the Lth multiple of the photon anisotropy today. So the photon anisotropy today is a delta T over T and is a function of angles. And if I expand this function of angles in multiple space, I will get this theta L of x. So how do you compute this quantity? In the old days, in the historical code cosmics, the goal was just to compute the transfer function that we have seen in module C, so the quantities which are in the Boltzmann equation, until today. So you would expand your photon temperature perturbation in a hierarchy of multiples going from the monopole up to L of 2,500. You would integrate these 2,500 multiples until today, and the value today would be directly this function. And this means that you have to integrate very precisely a very large number of variables. So the breakthrough was this idea of Selchak and Zeldariaga of 96 to use what is called the line of sight integral. The name is a bit ambiguous because line of sight integral, you would say, I integrate my quantities in real space along one line of sight. But if you look at this integral, it's an integral over time, but not in real space, in Fourier space. So it's a line of sight in Fourier space. It's a bit complicated to imagine, but you can see it differently. You can just say that this integral gives you an exact implicit solution of the full Boltzmann equation. That's another way to see it. So once you have written the Boltzmann equation, by playing with integration by parts, etc., you can see that if you plug this function inside the Boltzmann equation, you get an exact solution. And so this equation gives you the harmonic photon transfer function as an integral in which you get one of the source functions discussed previously multiplied by a spherical Bessel function. And the role of the spherical Bessel function is purely geometrical. The spherical Bessel function tells you how you project a plane wave in harmonic space. So it plays a role of projecting from Fourier space to spherical harmonic space. Okay, and the advantage of using these methods is that now if I want to compute my CMB, I only need to know the source function instead of 2,500 quantities. And this source function depends only on the very first few multiples of the photon in the Boltzmann hierarchy, as well as the baryon velocity, divergence, and some metric perturbation. So this source function only depends on a few transfer functions in Fourier space, like 5 of them, multiplied by thermodynamical variables like the visibility function. So you only need to integrate your big system of equation in order to get precise prediction on the first few multiples, and then for free, you get your CLs up to very high L. This is the magic of the line of sight integral. But so a Boltzmann code has to do this line of sight integral in this form or another form at some point. And this will be done in a separate module of calculation of transfer functions in harmonic space. I wrote the formula here assuming no spatial curvature, flat space. But in fact, when you go to curved space, you can keep the same logic. What changes when you have curved space is first that you have correction terms in your system of perturbation equation. The one solved in module C has got extra terms. And moreover, at this step, the line of sight integral, you have to replace your spherical Bessel function by more complicated generalized Bessel function, which are a bit cumbersome to compute, but all this is implemented in common class with different methods. Okay, so this step is really important and takes time also. Once you are done with this step, there is a little bit more to say. Yeah, very quickly you realize that this way of expanding the solution is not only useful for the CMB, but comes very naturally for the large-scale structure. Because when you want to compute the harmonic spectrum of cosmic shear or galaxy clustering, you naturally tend to get an expression with a similar integral. So for the large-scale structure observables like cosmic shear, CMB lensing, and number count, you have to do a similar line of sight integral. And in this case, the source function will essentially be the matter fluctuation or the metric fluctuations plus some small corrections. So for instance, for CMB lensing and cosmic shear, this S is just the sum of the two metric fluctuations, phi m psi, multiplied by a window function, by a kernel, which tells you to which redshift your lensing is more sensitive. And the kernel depends on the source, on the fact that you are talking about the lensing of the last scattering surface or of galaxies located at a distance, at a given distance. If you want to compute the CLs of density fluctuation, or more, you would say more precisely, the number count observable of galaxies, then you will use a formula like this, but now your source function will depend on the matter density fluctuation, or more precisely, as we said before, the baryon plus cold dark matter density fluctuation, multiplied by a selection function, which is just a modeling of how many galaxies you have in your bin and what is the redshift distribution of the galaxies in your bins. So you see that the formalism to compute CMB and large-scale structure observable is really the same with just different kinds of source functions here. If you want to compute your CMB lensing or cosmic shear or number count CLs, this is the right place also to use a nonlinear correction factor. And you write your source function as a linear one, and if relevant, you multiply by the nonlinear correction factor. So for instance, this is the CLs of cosmic shear. It's a lensing potential spectrum of cosmic shear, assuming that you have done tomography and you have binned your lensing data in 3 bins with and without taking nonlinear corrections into account. So all these tasks are done in module F. And then in module G now, you are ready to compute your CLs by just integrating over K the product of two transfer functions times the primordial power spectrum. So in the full general case, there should be a sum here because it's the right time to sum up over different initial conditions, adiabatic and isocurvature, and also over modes, scalar and tensors. And so for instance, suppose you have adiabatic and isocurvature modes, you would have to take into account the autocorrelation of the adiabatic modes, and then you would have two adiabatic transfer functions, the autocorrelation of the isocurvature, and you would have a cross term where you would take here one adiabatic transfer function, one for the isocurvature mode, and a cross correlation spectrum. But in simple cosmology, it will not be the case. You will only have here the scalar adiabatic mode, and you will not have the sum over ij. Still, you will have two indices here because you could compute temperature or temperature polarization, TE, or galaxy correlated with cosmic shear. So it would be an index here for number count, an index for cosmic shear, and you would multiply the transfer function of number count and cosmic shear. So the code can do all these things, all these cross correlations. And so it gives you many CLs, and this is a famous plot in which you decompose your CLs in the contribution from tensor, scalar temperature, tensor temperature. And then here you have scalar polarization and tensor polarization, etc. Okay, so after this stage, you have all the CLs that are predicted at first order in perturbation theory, but they neglect lensing effects. And if you want the lensing of the CMB is a second order effect, and you need some post-processing. So there is a last module here labeled with an H, which is when you compute the lensing of the CLs. So how does it work? If in your input you asked LCL, lensing CLs, then the code kept track of the metric fluctuation phi m psi in step C. And at the end of step C, it even stored phi m psi as source functions. Then later on, in the transfer module, it will combine them into a lensing potential source function and then transfer function. And in the previous step, it will then infer from this CL phi phi, which is the lensing potential spectrum. On the other hand, if you ask for CMB observables, out of many fluctuations in the module C, the perturbation module, it will store the CMB source functions. With the CMB source function, it will compute some CMB harmonic transfer function, and then in the previous stage, the unlensed CMB spectra. And then the role of this final module will be to do several summations over combinations of the two kinds of spectra in order to give the lensed CMB spectra. And for this, we use the same formalism, not the same numerical implementation, but the same formalism as Lewis and Chalinor 2005, which is a full sky approach. And so, for instance, in this plot, you find the lensed versus unlensed CLs. The unlensed one are in red, the lensed one are in black, and you see it's very difficult to see the difference, but as you know, lensing tends to smooth out features. So the lensed one has smoother extrema. So it's easy to see that the red is the unsmoothed version and the black is a smoothed version. Okay, so any modern Einstein-Boltzmann code must at least go through these steps from A to H. And you see that they can really be done sequentially. Now, all this would be like a very general introduction on how to compute perturbations in cosmology, linear perturbations. Now I will try to wake you up by giving more specific details, which are more specific to class, about the less trivial aspects of of each of these steps. So the step A is anyway, oops, going too fast. The step A is anyway rather trivial, the background integration. But maybe you want at some point to complicate your cosmology. You want to code something in which the background evolution will be a bit different. I take an example. Maybe you are interested in a non-trivial model where baryons are coupled with dark matter. And then the evolution of the baryon temperature is non-trivial and must be integrated. While in lambda CDM cosmology, the temperature of baryons has a trivial evolution that you know in advance analytically. So you must add a new variable to your background module. How do you do it? If you want to do it one day, you have to understand that the background module tries to formalize things and define three types of background variable called A, B, C. B are the most important. B are the quantity that you absolutely need to integrate over time, otherwise your code makes no sense. So here I take the particular example of the lambda CDM model, and it would also apply to many trivial extensions. There is one quantity that you have to integrate over time. It's the scale factor. The main goal of the background module is to integrate the scale factor. If you never do this, you will never be able to solve your cosmology. And you will integrate your scale factor by a differential equation, dA over d tau. And this is just coming from the definition of H. If you use conformal time, then H is A prime over A square. So the equation you want to integrate is dA over d tau equal A square H. So in lambda CDM, there is only one variable B because you only need to integrate one differential equation. Now, if you want to integrate this differential equation, on the right-hand side, you must evaluate H. But H can be evaluated analytically as a function of B, which is A, of the variable of type B, which is a scale factor. Indeed, H is made up of a sum over many functions, which are all functions of B variables. So A is the ensemble of functions that have a direct analytical expression as a function of B variables. And in lambda CDM, these are, for instance, all the densities, all the pressures, and the Hubble parameter. Because the Hubble parameter now can be expressed using the Friedmann equation as a square root of a sum over the densities corrected by the curvature effect. And the reason for which all these are analytical function of A is not fundamental. It's because in lambda CDM, we assume a trivial evolution of the background quantities. We know that our non-relativistic species have a density scaling like A to the minus 3. Our relativistic species scaling like A to the minus 4. And lambda does not scale. So in lambda CDM, we can really express everything as a function of the scale factor. And ultimately, it's just the scale factor that we need to integrate over time. C are less important. C are variables in which you realize in the course of the code that it would be nice to know C, but for this you need to solve another differential equation with respect to time. But it's not strictly speaking necessary for the logic of the code to work. So in class for lambda CDM, there are three variables C. There is a proper time, the sound horizon, and the linear growth factor. The proper time is obtained, just for your curiosity at the end, by integrating dt over d tau equal to the scale factor. And here we have a function of the scale factor because it's a scale factor itself. Next, the sound horizon is useful for BAO, for instance. You don't need to know it. You can compute the CMB without knowing it. But in a BAO likelihood, it's nice to know the sound horizon. And the sound horizon is obtained by integrating over conformal time the baryon photon sound speed, which is an analytical function of A. So in summary, C are variables which are useful to integrate, but are not used to compute A. And so you could do everything with only A and B. So you wonder why I bother you with this. It's because when you will have a more general cosmology, the first thing you need is to figure out if your variables are A, B, or C, because depending on this, they will go in different arrays, they will be declared in different places, and they will be solved in different functions. So to see if we understood, let's take more complicated cosmologies. So I will take first, this has a kind of little inertia. I will take first the example where I have a fluid. So in class, you can always switch on a fluid, and then you decide if you want to use it to simulate simple dark energy models or funny dark matter models or self-coupled dark radiation fluids. In this case, if the equation of state of the fluid is trivial, for instance, is a constant or a very simple analytic function, then the density of the fluid can be integrated analytically. And then you could say that the density of the fluid has an analytical function as a function of A, and you would put it as an A variable. But this works only if the equation of state is simple. If you want to be general and allow for arbitrary equations of state, then you must recognize that you now need one more integral over time to get the background fluid density. So you will do this, and then you will say that you have a new variable A, which is W of A, and a new variable B, which is rho. And the variable rho is integrated with d rho over d tau equal to this equation. You recognize it. It's just using the conservation of energy. And it really matches our definition because on the right-hand side, we only have a variable, which means we only have functions, analytic functions of A. So the code can work with this logic. Now let us take another example. No, yes. This one is more tough. Suppose that you want to switch on quintessence. So I told you quintessence is also implemented in class. When you have quintessence, the evolution of your scalar field is given by the Klein-Gordon equation. It's a second-order differential equation. And the logic of the module A is to use only first order. So we are going to split it, as usual, in two first-order equations, which means that we must have two variables of type B. One gives you d phi over d tau, and one gives you d phi prime over d tau. And the Klein-Gordon equation is here. Now, in the Klein-Gordon equation, what do we have? We have functions of A. Very good, they are A variables. We have phi prime. Yeah, phi prime is a B variable. And here I am allowed to have any function of B variable, so it's okay. And then I have the potential term, which is a function of phi. So I should just define my potential as an A variable. It's really an A variable because it's a function of a B variable. And then the logic of the module is respected. And as soon as you found a way to respect this logic, your coding goes very fast. There are guidelines in the code saying, please declare here your A variable. Please set up initial conditions for your B variables. You notice that I also define the density here because at some point in the Einstein equation, I must know my density of scalar fields. And the density of the scalar field is given by the kinetic and potential energy. So it's still an analytic function of B variables. I am safe with my logic. If not, I will need to change it until I am happy and I fulfill these criteria. Okay, another example, decaying dark matter. If you have cold dark matter decaying, for instance, into dark radiation, then you have usually, assuming that especially if the decay rate is non-trivial, you must solve a new differential equation to get rho of decaying cold dark matter, rho and the rho of the dark radiation, which is created out of the decay. So you have added new B variables. And for instance, the equation of evolution for decaying cold dark matter is this one. There is a first term that would give you an a to the minus 3. And then there is a term showing how much you lose from the decay. And we don't need new A variables because here we have already everything we need. Yeah, this gamma A, this interaction term, should be added here as an A variable. I forgot. Okay, so this is what you know if you want to be efficient in modifying the background module. Now, thermodynamics module. The thermodynamics module needs to integrate over a combination and get variables like temperature and ionization fractions. And the option which is inbuilt in class is an improved RegFast, which has been maintained and improved until 2008. Because this is historically a very fast code, and after this improvement of 2008, it was proved that RegFast had enough precision for the needs of Planck. It doesn't mean that it has enough precision forever, and anyway, class gives you the opportunity to switch to more precise codes. So there is HiRec, written by Yassin, who is one of the organizers of this event. And there is CosmoRec, written by Jens Schluba. When you download class, you download a version of HiRec together with it. And HiRec is written in C and in very nice style. So it was very easy for us to interface. And in the input parameter file, you can switch a flag, and then class will use HiRec. For CosmoRec, the interfacing was a bit less easy, I must say, but has been done. You still need to download CosmoRec separately for the moment. And then you switch a flag and CosmoRec will be called. And things will happen for HiRec and CosmoRec. I believe that they will become faster and better integrated with class. These are in the plans. Okay, this is what I wanted to say about thermodynamics. Now, another point. When you compute recombination, you need to make an assumption about the primordial helium fraction, the famous 0.25. It's closer to 0.25 than 0.24, even if many textbooks still talk about 24. So you need to make an assumption here. And in the input file, you can assign a value to your helium fraction, or you can write that the helium fraction is set to BBN. You see that there is enough flexibility in the input such that the same name can be associated to a number or a string. And the input module of class always will make sense of it. It has been written for that. If you set it to BBN, it means that the code will check what is the value of omega B and NF that you ask. And then it will do some interpolation in a pre-computed table that was produced with a BBN code. For us, it's Parthenope. And this will tell you what is the value of helium that should be associated to your input NF and omega B if you assume standard BBN. So by default, the code will behave in this way. It's more accurate, more realistic. But this BBN table has a finite range for the interpolation. So if you play with extreme and physical values of omega B and NF, you will go outside of the interpolation range. The code will complain. And then if you want to avoid this situation, you should set it manually to some value. The interpolation table is located in a directory. And from time to time, we update it because the BBN codes are also making some progress. So at some point also, we will update this table because there has been a new version of Parthenope and new measurement of nuclear rates. Okay. Next, in the perturbation module, I can say something about the polarization hierarchy. So when we developed class, we did not only try to write a structure code, we also worked on the underlying physics, and we did some progress in this respect, and this is one example. So if you want to compute polarization, you need to write a Boltzmann hierarchy for polarization, like you did for temperature. In the old approach of Mayen-Bertschinger, there were two hierarchies, one for temperature with coefficients F, one for polarization with coefficient J. And then if you stick to the use that Seljak and Zaldariaga have made of Mayen-Bertschinger formalism, they give rise to a source function for T and a source function for P. And then Uros and Matthias showed that if you have these sources, by convolving them with different Bessel functions, you will get a harmonic transfer function for T and for the E and B mode of polarization. What is interesting is that you get all your output with two Boltzmann hierarchies. So if you integrate up to an L max of, say, 100, you have 200 equations. When you and Martin White did a very nice work in 97 that was more general because it also dealt with scalar, vector, tensors, flat, open, and closed universe all at once. It's called the angular total momentum method, the total angular momentum method. And they found that you need to write three hierarchies, one for temperature, one for E mode, one for B modes. This is what came out of their equations, in particular because they had a curvature in their equations. And out of this, they showed how you can define a source for T, E, and B, then a harmonic transfer function for T, E, and B. But in this process, you have introduced three hierarchies. So in my example, it would be 300 equations. Then in CMB fast, the strategy was the following. CMB fast acknowledged that this is faster, so there was a switch. CMB fast said, if you have flat space, use two hierarchies. If you have curved space, use three hierarchies. The authors of COM said, but this is not nice. We want everything to be continuous. Otherwise, we have like the numerical error between the flat and non-flat case. We'll have a non-continuous jump. It's not nice. So we will always use three hierarchies, even if we have more equations. It's a good reasoning, but with Thomas Tram, when we encoded curved space, we thought there was no reason for having one more hierarchy, just because you have changed the geometry of the universe. There is no logic. So we found a way to rewrite everything sticking to two hierarchies, also in curved space-time, through essentially more by finding some new kernels in order to go from this step to this step, which are valid also in curved space. So class will only use two hierarchies, but it can be interesting for you because if you are a CMB physicist and you try to match equation in COM and class, you will not succeed because in COM you will always find the three hierarchies, in class the two ones. So our Boltzmann equations are really different. And this is why comparing the two codes is also a true test of accuracy of the two codes. Okay, there are other things to say about the perturbation module, like the fact that there are approximation schemes. They are described in the class 2 and class 4 paper from 2011. Not much has changed since then. This is the space in which I want to follow my differential equations. Here I have my Fourier wave numbers, and for each Fourier wave number, so each vertical line, I want to integrate my perturbation starting from the primordial universe and until now. There is a line which is the Hubble crossing line. And my goal is to go fast, and in order to go fast, I should start integrating late. And this is the line of initial conditions. Initial conditions, so the integral for a given mode starts on this line. If it is a large wave number, the condition is that you should start sufficiently before decoupling, and decoupling is this line. If you don't start enough before decoupling, then you don't start from the tightly coupled regime between photons and baryons, and your initial conditions become ill-defined. So this is why there is a horizontal line. Then there is a line here parallel to Hubble crossing, because if you deal with a small wavelength, there is a stronger condition that you should start when you are well inside the Hubble radius, because well inside the Hubble radius, the evolution from inflation until this point was almost zero. Everything was almost frozen and can be approximated analytically very well. So for each mode, you start from a point on this line, and then you go down. And fortunately, you can use approximation schemes in different regimes to speed up the calculation. Otherwise, the codes would be very slow, because at each time and for each mode, you would have of the order of 1,000 equations. And you don't want that. You would like, when possible, to reduce it to, say, 10 equations or less. So you can play with different things. The tight coupling approximation is a way to reduce the photon and baryon equations to only 4 equations instead of 1000, using the fact that they form a tightly coupled, almost perfect fluid. It's very well known. So class does this approximation at second order. Why second order? Because if you do it at a higher order, you can start later, because you capture better the deviation from perfect tight coupling. Then if you have ultra-relativistic particles like massless neutrinos, you realize that they are cumbersome to integrate, but when you are sufficiently inside the Hubble radius, you can simplify your equation without making a big mistake in the following way. So the massless neutrinos, in principle, should be followed like the photons by an infinite hierarchy of equation. It's a collisionless Boltzmann equation, a Vlasov equation, and you should take a large L max in your system. There is one way to approximate Boltzmann equation by the equation of an imperfect fluid by truncating the Boltzmann equation at a low L. If you truncate at L equal 2, it's really an imperfect fluid, but it's always very bad for massless neutrinos. So you could see, may I truncate at 3 or 4 or 5, and it depends when you do the truncation. The longer you wait, the smallest is the L at which you can make a truncation without producing a big error. And what we choose is to wait until we are sufficiently inside the Hubble radius, and then we truncate the Boltzmann hierarchy at the level of 3 equations. This is something that Wayne Hugh had tried in the past in a paper called Generalized Dark Matter. We managed to kind of improve this for massless neutrinos. And so when we enter the red region, the number of neutrino equations go from a few dozens to 3. And finally, there is a last approximation called the radiation streaming approximation. And it applies to both photons and massless neutrinos when you are at late time during matter domination and well inside the Hubble radius. In this case, you know that you can view photon and massless neutrinos as test particles falling in the gravitational potential well created by baryons and cold dark matter, but without a significant feedback on this gravitational potential. And from this physical intuition, you can build up some approximate equation for the photon and massless neutrinos, which are not differential equation, but constraint equation. So just give the photon and the neutrino density as a response to the gravitational potential. So this is this radiation streaming approximation, and it removes completely the photon and massless neutrinos. So to summarize, when you are in the TCA approximation here, you don't have so many equations. Essentially, you only have the big hierarchy of the massless neutrinos. This hierarchy disappears in the red region, and the photon hierarchy disappears in the magenta region. So the region in which calculations are a bit cumbersome are these bonds, plus a bit of the red region here, but it's not much. This region here is super fast. This one is super fast. This one is quite fast. This one is quite fast. And this one is slow because there are no approximation. Outside the Hubble radius, it's always fast because there is no oscillation. So the most cumbersome is a white region. But you see that you have reduced a lot the region in which you have lots of equations. And this is a very decisive ingredient for making the code fast. We have coded these approximations in a formalized way, meaning that it would be easy for you to add a new approximation. It means that, again, this is not hard-coded. We have a special syntax where we define a list of approximations. Each one has a dynamically allocated index, and the code loops over this index to determine approximately when each approximation should be switched on and switched off. And when you switch approximation, how should you copy the previous system of equation to the new one? It's really very formalized, such that adding a new approximation is like adding a new species. You follow the same syntax as for the existing one, and you get the same logic. Okay, I had a few more, so I will finish this lecture. You see, I have a few more slides. I will finish this lecture after lunch. Do I want to finish on C first? No, this will be perfect to start with after lunch. So we will finish the theory part after lunch. Do you have questions on this? No? Okay, very good. Time over. Time for food. Thank you.